So we've covered a lot of ground in the Chapter 6 in class problems 1 and 2. And so to kind of summarize and remind you of the things we've done, I want to go over a recap. Okay? And so what we wanted to do is we wanted to quantify how changes in volume and temperature affected our internal energy. And in order to develop a sort of model to do that, we needed to apply the calculus of thermodynamics. Right? And we saw that when we were dealing with a closed system that underwent isothermal compression, we derived that the change in internal energy, or the partial derivative of internal energy with respect to volume at constant temperature, was equal to this relationship, which is expressed only in terms of pressure, volume, and temperature. So things that we can measure. Right? To figure out this dp dt at constant V term, what we did is we just plugged in different equations of state. When we plugged in the ideal gas law, we saw that this partial derivative is exactly 0. And that matches what we assumed before, that if we have an ideal gas and temperature is kept constant, that the internal energy is maintained. All right, but if we applied a more complicated equation of state, the van der Waals gas, we saw that even if we kept the temperature constant, that what happened is that we saw that our internal energy actually decreased. Okay? All right, and so, that's what mathematically we saw from our analysis. But what does this all mean? In general, so to tie it back to the molecules in our system, in general, molecules like minimizing or decreasing their energy. Right? And I'm just telling you this now, but we're actually going to show in chapter 7 why they like doing this. Okay? So in general, molecules want to have the lowest energy possible. Okay? And so that's why when you do this compression, the internal energy wants to decrease. We also saw that this decrease was proportional to that A parameter, right? And that describes the strength of interactions between our molecules. Okay? Right? And we saw that, when we switched from nitrogen to carbon dioxide, and carbon dioxide had the larger A value, that proportionally, carbon dioxide had a larger decrease in that internal energy. And so, from using the van der Waals gas equation of state, we could see how these molecular interactions affect the internal energy of our system. We also saw that the work needed to compress the system was also affected by our A and B parameters. Though, even in the case of work, the A parameter had the more significant contribution. Okay. All right, and so, in this problems 1 and 2, what I wanted to demonstrate to you is how, we could take systems that we've sort of thought about before, but we can analyze them in a more rigorous way so that we could understand how, the chemical identity or how the interactions between molecules and the size of molecules, how that actually affects, the amount of heat we could extract out of a system.